Good afternoon. Professor Gopalan Rajaraman completed his PhD in 2004 from University of Manchester. Then he did a couple of postdocs with very good fellowships. He was an Alexander Van Humboldt Fellow, and he was also Marie Curie Fellow. He joined our department in 2009 as assistant professor, and he is currently a professor, and he has received a large number of awards. He is a Swarna Jayanti Fellow in 2019. Then he is a Young Scientist Medal. He got a Aura A.V. Ramarao Young Scientist Medal, IRCC Young Scientist Award, and he has got several of those things. He is currently a chair professor in our department. So with this brief introduction, I will ask Professor Rajaraman to.
Thank you. Thanks a lot for the kind introduction, and let me thank the IRCC for choosing some of our, or actually the review paper for the award. You can see that I just made that title very general. We have been working in this area of molecular nanomagnets. Our tools are essentially to use, ab initio KSSAF calculations, state-of-the-art calculations, which can be used to solve some of the problems. I'm just going to kind of give you a glimpse of this area and what is that is summarized in the review. I think that is the whole idea of this talk. Before I begin, I like to thank the students. Many of them are here who have actually contributed significantly to this review for which the award is given, and also to our research, which have been ongoing for the last 12 plus years. Also the funding agency coming from ACRB, IIT Bombay, and computing facilities as well. These are the three actually, review and book chapter that we have written. So of course, I would not have time to actually talk about all that. I'm going to just concentrate one of the recent review that we have written on magnetic anisotropy, and I'm just going to kind of give you a very brief glimpse of in this particular review. Before I talk about magnetic anisotropy in molecular magnets, it is important to also kind of, looking at the wide audience, I just wanted to give you very brief introductions into what is molecule-based magnets. Magnets, I think, is everybody knows already. Refrigeration, so you have a fridge magnet. A permanent magnet is something that we all are familiar with, where you have a material like magnetite, where you have billions of metal atom, like for example iron +3 and +2 oxidation state. They couple ferromagnetically, meaning unpaired electrons are pointing in the same directions, gives rise to a very large magnetization. It means that all the electrons arrange in the same directions, so there is a resistivity to going up to down. So then they stay in the same direction. This is what is called permanent magnetization. But technological application now demands that this magnet needs to be created at a very, very, very small level. The smallest level that as a chemist we can think of is of course molecules. Is it really possible to create a permanent magnetization at a molecular level? So that is the idea. Well, what is the challenge? The challenge is that if you look at the physics of the macroscopic system, the permanent magnet, you have spin 10 to the power 20, that many unpaired electrons, which are not paired, that many are required to actually create permanent magnetization. So that is how the fridge magnets are working. But if you actually do the down scaling of the particles, if you go from, let's say, macroscopic to mesoscopic, where you're looking at nanoparticles, this is the current technology that is used in the hard disk, we have about 10 power 5 to 10 power 4 number of ions. That many spins are required. If you go further down to molecular cluster or individual spins, that number of ions, the spins are very, very small, and it is very difficult to create a permanent magnetizations, the spin that does not flip. So that is a challenge. Of course, why we are doing this, that idea is that if we can achieve that, we will be able to use it for potentially for a lot of application. One of them is solid state hard disk. Current technology is about 1 terabyte per inch square. If we can achieve SMM, it can actually take up to 10 to the power 100 terabyte per inch squared. So that can actually increase tremendously the storage density. That is the whole idea. So this is somewhat kind of a comparison, I would say. Superconducting magnets is something that probably many of you are familiar with. So superconducting magnets started discovered in around 1900 when they were working at extremely low temperature. And then now you can see there is a tremendous growth over the years, and it hit at liquid nitrogen temperatures at around 75 years. It took about 75 years before we can actually kind of create a magnet that has a potential applications. Now it is used everywhere, from MRI to all different applications. You have superconducting magnets. If you look at the single molecule magnet that I'm talking about today, molecule-based magnets, the first discovery was made only in 1993, and already within a period of 25 years, you can see that there is a tremendous growth. Already liquid helium, liquid nitrogen temperature is reached. So this is something that shows that this class of molecules have great potential applications in the years to come. So how do they work? So then only we can figure it out. So the first single molecule magnet is essentially an inorganic complex. What you see here is a molecule with lots of spins, that where you have is a manganese, a metal in the middle. You can see this pink color balls, and decorated by an organic ligands. So you have a metal and organic ligand surrounds and make one complex. And that complex, if you can actually look at the spin, you have a ferromagnetic coupling between the metals of outer ring, and antiferromagnetic between outer and inner ring. You can see the spin up and spin down. So this gives rise to a very, very large spin ground state, meaning this molecule has 20 unpaired electrons in its ground state. It is not very large like nanoparticle, but it is sufficient enough to give you a barrier for going up to down. This is the first molecule. You can see that if the spin has to relax from here to here, it has to go from here all the way up. All this energy level it has to cross and then go down. This gap, which is very, very important, of course, is what we call zero field splitting parameter D. So this D parameter, if we can enhance, we can raise the barrier height. There is already theoretical foundation which suggests that the barrier for reorientation, this is going up to down, is S squared times D. S can be is this ground state, so it is already large. We can increase that, but what is difficult here is to increase the D, which is 0.5 wave number, very, very small. If you look at this case, like you can see that S is 10 to the power square, 100, but then this is very small. So that is why the barrier is not large enough. So can we control the zero field splitting, the ZD parameter, the anisotropy? That is the whole idea of the review that we have written. What is zero field splitting? If you have a simple mononuclear cobalt 2 complex, okay, so hopefully you all are familiar with it. So it's a D7 electronic configurations. If you have a D7 electronic configurations in this crystal field, it splits into two types. Orbitals are split into T2G and EG. So you have 3 unpaired electrons which are not paired, 1, 2, and 3. With the 3 unpaired electrons gives rise to a ground state of 3 by 2. This 3 unpaired electron decides, the ground state. When you have this kind of a degeneracy where this electron can be here, or it can be here, or it can be here, this rise to a spin orbit coupling. So what happens is that S equals to 3 by 2, which splits further into a plus or minus half, or plus or minus 3 by 2, or plus or minus 3 by 2, and plus or minus half. These are the two different ways the MS level splits. This is the microscopic quantum number related to S equal to half. S equal to 3 by 2. So if a large MS value comes down, so the D value we are going to call it as negative, and if it is smaller MS comes down, it is positive. So to have a magnet, you can see that you must have a negative sign. So we need to have a sign negative, we must have a large D, which is the gap between these two levels. If you have that, we can have a very fantastic magnet. So that is the idea that we have been working with. So now what what controls this parameter? So that is the very important parameter, the D parameter. What decides the sign? If you look at this again, energy level splitting, very simple crystal field splitting of the energy level. This is the ground state, geometry. When you have excite one of these electron, let's say from dxz orbital, one of this orbital to the other orbital, this contributes to negative d. Why? Because this dxz and dyz are same angular momentum operator, that is plus or minus 1. ML level is plus or minus 1. If they are between, the transition is between the same, the d is negative. If the transition is between different ML level, for example, xy to yz, xy to yz. So this is plus or minus 2, this is plus or minus 1, this contributes to positive D. So we understood that by doing, of course, ab initio calculations and ab initio Cassisafe calculations, which are instrumental in actually predicting the accurate D values. So now what do we do? So we understood that what is the sign and magnitude of D corresponds to. We obviously want to have only one metal, and we want to have a very large negative zero field splitting D parameter. So what is the combinations of the ligand field and metal, if you put together, what combination would be best suited for a best magnet? This is what we have summarized. If you just take a cobalt free ion, no ligand, of course you have a spin orbit coupling of 533. You add 2 ligands, some organic ligands along particular directions. You have a linear geometry, cobalt 2 plus 2 ligands along the linear geometry. You have a crystal field, something like this. you can see dxy, x squared minus y squared and xy, same ml level. These electrons can go here. So this means that it will result in a huge negative zero field splitting. Same ml level, same transition, very less gap, huge negative D. So we suggested that this could be a very interesting target to make actually single molecule magnet. Well, already there are somebody has made that. You can see this is a 2 coordinate linear cobalt with the highest blocking barrier was reported by Jeff Long. Okay, so we'll keep moving further. So we can actually add one more ligand. So make it 3 coordinates. So this is what the chemist does. Like try to kind of extend the ligand framework. You can have a trigonal planar geometry. The orbital diagram that I have drawn here suggests that the trigonal planar can have neither, a moderate d value, not so big, can be, moderate d, but it can be negative or positive. Again, this is reported by Ishwar, who has actually made this 3 coordinate with a d value of about 54. So this is quite good, but sign is not pleasant because the geometry is not favorable, but then still the magnitude is quite good. So 54 is something that we could achieve. So we keep going. So we add one more ligand. This is 3. Now we have 4 ligands. There are 2 different geometry possible. One is tetrahedral. There's 4 ligands in this tetrahedron fashion, or distorted geometry of tetrahedron. If you have a tetrahedron, you can have a small d. You can have a plus 10 and minus 20. If you have a D2D, you can see, I need another 1 minute. So you can have a D2D, which is, you have a very large negativity. So this is also again, already kind of taken a cue from the theory that somebody has looked into the geometry and then tried to kind of make this parameter larger and larger. We can keep going. We can do it for 5 coordinate. That already geometry is good, but not sufficiently large. You can make it 6 coordinate, 2 different geometry, octahedral. And you can have a trigonal prism. Octahedral will give only positivity. Again, there are examples, so many examples are there in literature. And if you have trigonal prism, it will be negative D. Again, this is also, reported. So we can keep going to 7 and 8 coordinate. 8 coordinate also gives only positivity. So whatever we are just writing based on the calculation for different coordinate geometry is what is already reported, or several experiments over the years able to see this, the sign and magnitude are correlated. In nickel, we have seen that, if you have a trigonal bipyramidal geometry, there's like 5 ligands, you can have a huge zero field splitting, about minus 540. This is really the largest that we could actually come up with. And this is again synthesized and reported with our, help from calculations. So that brings to me the summary. So I just tried to tell you that this ab initio Kassav calculation is somewhat like this one, that you can use this like a magic. And this is the rabbit, this is the single molecule magnet, just one metal ion based magnet. So it is possible to actually predict what combinations of the metal and ligand one can use to come up with a large D. We have studied more than 100 structures. That error is within about 10% in the magnitude when you compare to the experiments. And very large D is reported, when original manganese 12 has mainly minus 0.5. And now we are reaching up to minus 600. So there is like tremendous value is already achieved using this, Kassav calculation. So this is the review that, we have written, and, I like to thank you all for your